Lyon, the Institute of Chemistry in Lyon, which is now known for catalysis. And they didn't have a fellowship for me, so I decided that I'll do my work whenever I can, and Stiglitz consented to it and suggested that I should work for Maurice S. Karash. Anyway, I had a job, then lost a job, then I had another job that didn't pay me, so I looked for another job. Finally, I was without a job, so somehow someone mentioned that UOP was looking for a chemist, part-time, to do some analytical work. I went to UOP, was interviewed by a man by the name of George Murphy. He accepted me, although he did not believe that I'm telling the truth, that I'm going to the University of Chicago, because he said no one ever that he knows of could get a PhD working part-time. So he called up Julius Stiglitz, and Stiglitz recommended he should take me, although he recommended me reluctantly because he did not feel that one should, that UOP would be the best place for me to work. He told me about it years later. But anyway, I got a job in an analytical lab, a routine lab, to analyze gasoline which came from cracking of oil. This was thermal cracking. Catalytic cracking was not known at that time. And I was supposed to determine the amount of unsaturation in the gasoline. And this involved treating the gasoline, a portion of it, with 96% sulfuric acid at ice temperature by shaking a calibrated burette, or was calibrated cylinder, and determine how much of the oil, hydrocarbon, went into solution. And this, I had to record it, and after a certain period of time, the disappearance of hydrocarbon, the upper layer of the mixture, determined the amount of unsaturation. I did it for a while, for about a week, 10 days. It was awfully boring job. So I decided to do some research. And I let it standing longer and longer, and found out that after standing for a while, at the end of the day, the amount of hydrocarbon in the upper layer augmented. So I decided to shake it again. I thought maybe some of the olefins separated, but none of them separated, and the amount of upper layer remained constant. So I repeated this the second day, the third day, and found there was something wrong there, that either the olefin were transformed to saturated compounds, or maybe some of the saturated compounds separated, but they did not go into solution anymore. So reluctantly, I reported to my supervisor, who was not too smart, now I realize, and told him about my observation. He was very much upset about it. They have been doing this for years. No one complained about it. So he said I should go and do the work and not question it. I apologized and went back to my work. But a couple of weeks later, I found something else, and reported, and the company was interested in it, found that this happened to be a patentable observation, and they should let me to research lab. A few months later, we were told that an important man from Russia is coming. We should clean up the place. And I was introduced a few months later to Ipatchev, who came with the retinue of the people from administration and with some of his Russian-speaking people. And Ipatchev, who did not speak English, I spoke just a little bit of it, but I spoke French fluently, he spoke French somehow, and were able to converse. And I told him about this observation, that we have a problem there with treatment of hydrocarbon with sulfuric acid, and he said that, all right, we'll try to investigate what happens. Ipatchev left back to Germany when he had a contact with Badische Anlagengesellschaft, and eventually, a year later, he came there permanently to UOP. So we started to work on this problem. This led us to discovery of conjunct polymerization. We worked with pure hydrocarbons, with olefins, paraffins, others, and found that olefins actually are being converted to saturated hydrocarbons. And this is conjunct polymerization, which is probably the foundation of all the catalytic reactions of hydrocarbons using strong acids, in which olefins are converted to saturated hydrocarbons and to some kind of a sludge which complexes with sulfuric acid. And later on, this sludge serves a good purpose too in certain reactions that we'll discover later on. Now we realized that since olefins are converted to paraffins and to others and cycloparaffins, some of them were cyclohexane derivatives, we thought that maybe paraffins are not as active as they should be, and they might also probably undergo other reactions. Working with sulfuric acid and with mixture of hydrocarbons, we discovered, although it was not known, that at that time the sulfuric acid is an alkylation catalyst where aromatic hydrocarbons can react with olefins, not with ethylene, not with propylene, but with higher olefins like butane and so on. Ethylene and propylene do not undergo polymerization with sulfuric acid. We found out that ethylene with sulfuric acid forms diethyl sulfates, and propylene forms also mono and diisopropyl sulfates. So, but with butylene and higher reactions, higher olefins, for both polymerization and also alkylation of aromatics proceeds very well. Since olefins form paraffins, we thought maybe paraffins should also react with olefins the way other hydrocarbons do. And at that time, we also, since sulfuric acid was not too good a catalyst for many of the reactions, we decided to shift to other acids. We found out that phosphoric acid was an excellent catalyst for polymerization of propylene, because with sulfuric acid we could not go beyond room temperatures, and therefore the diatosulfates that was created, or diisopropyl sulfates, at higher temperature decompose, oxidize. With phosphoric acid, we were able to carry the reaction of polymerization of propylene at higher temperature, which eventually became a commercial process when phosphoric acid was converted with Kissel to silicophosphoric acid. However, we found, however, that aluminum chloride is a good catalyst, very active. We decided to try aluminum chloride as a catalyst for alkylation of commercial pentane, or we call it light petroleum ether, with ethylene. And sure enough, we found, using aluminum chloride, HCl and ethylene and this petroleum ether, that we were able to enter ethylene into a reaction. Later on, more careful investigation showed that we were lucky that the light ether contained a mixture of pentane and isopentane, and somehow isopentane mostly entered into reaction. Later on, we found out that isobutane reacted, and normal butane did not react in presence of ethylene. So this was the first observation that we made, that alkylation of paraffins is possible. However, the reaction of olefins with normal butane did not take place, but with isobutane reacted very efficiently. Luckily, in 1935, we discovered that normal butane isomerized to isobutane. At that time, we knew that isomerization is one of the reactions occurring in the presence of acids. We thus decided to see whether butane would react. So we took butane, hydrogen chloride, and aluminum chloride, and sure enough, put it in autoclave at a temperature of about 150 degrees, and sure enough, we got almost a large amount, about 30% of isobutane in it. Then, how this reaction, the combination of butane to isobutane, and also isobutane reacting with olefins, was the basis of the alkylation reaction that eventually was developed commercially.
No, the alkene, was that essential with the alkane, or?
We found, working with this, that we were able to identify the compound. We were able to, we saw the commercial possibility of. Eventually, other people were using other catalysts. Later, years later, was using HF. 96% sulfuric acid we found was not too good. Later on, it was found that 100% sulfuric acid was very good catalyst. But the first reaction discovery was made in 1932, in June of 1932, using light petroleum ether and ethylene. Eventually, we found immediately that isobutane was useful. The isobutane was the necessary hydrocarbon. And the detail, the reaction was then further investigated. Louis Schmerling proposed the mechanism of the reactions. This was in about 1937, 1938, after we discovered that butane can be converted to isobutane. although the company was not too enthusiastic about it, because they said who would ever want to use isobutane, normal butane we can add to gas in the winter time, it has low vapor pressure. Isobutane you cannot add to the gasoline because it has too high pressure. But when the war broke out, we realized that isobutane is the desired product of the reaction. By that time, we have the mechanism of isomerization of butane to isobutane elucidated, because in the presence of aluminum chloride we got erratic results. Sometimes we got good yields and sometimes poor yields, and systematic study revealed to us that in order for isobutane to isomerize, for normal butane to isomerize isobutane and vice versa, we needed traces of impurities. And we found, working on a high vacuum line under very highly controlled conditions, that under very pure conditions, in the absence of air, moisture, and so on, and having purified butane, that the reaction did not take place. However, when we added about 1000% of olefin to it, we got isomerization of butane to isobutane, and we elucidated the mechanism that goes to cation formation and to transfer reaction, iodide transfer reaction, we developed this process. But the basis of all this was the first reactions we studied at UOP, means reactions of olefins with sulfuric acid. This reaction showed that olefins are being converted to paraffins and polyolefins, and we call this reaction conjunct polymerization, whereby olefins are being converted to polyolefins and to some cyclic compounds which were sulfated and went into sludge with the sulfuric acid, and this sludge was, on decomposition, gave us highly unsaturated hydrocarbons which smell somehow like pine, has a terpenic smell. And the upper layer consisted of saturated compounds, paraffins, mostly isoparaffins, and cyclic compounds. And the results of this investigation was published in the first volume of Journal of Organic Chemistry under the title of Conjunct Polymerization, because later on we found out, and was found, that in order for alkylation to take place in the presence of sulfuric acid, you needed the complexes between sulfuric acid and the highly unsaturated compounds, because within this medium, polar medium, alkylation of paraffins and olefins proceeds. But the conjunct polymerization, whereby we're able to convert olefins to paraffins, gave us the idea that paraffins probably are not as inactive as the name paraffin means. Parum affinis, something very little affinity can be ascribed to hydrocarbons, that some hydrocarbons can react at -40 degrees.